Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back, folks, to episode 3, part 5, local metal loss. And in this video, we're going to look at example 5.2 of API 579.2, which is the problem manual that is the 2006 version in support of the fitness for service standard API 579.1. I'll be talking to the 2016 edition, and there's not a lot of changes, but I've also alluded to the 2007 version, which is the second edition. So what we're going to talk about is we're going to look more specifically at the groove-like flaw. And the next thing we'll do is we'll look at the example we'll look at is a two groove flaw one. So there's two grooves beside each other. They're very similar in size, but it just gives you it's been simplified to give you an idea on how to work that problem. And then finally, we'll do the level 1 assessment. So as per usual, we will begin with table 2.2, and we'll look at all of the mechanisms and try to pinpoint which ones are the ones associated with our problem. And this is found in chapter 2, and there's videos on that topic. In this case, all we have is part 5, local metal loss. So if you look at the diagram over to the right here, you can see the effects of two grooves. So basically that's the shape of the grooves that we'll be analyzing today. So there'll be one here and then one over here, and they're very similar in length. So and they're let's continue and we'll look at some more of this. So we want to look a little closer at table 2.2. So what do we see here? Well, we see a table here where we have a pressure vessel, and it's going to be a 516 grade 70 shell and head. The pressure is going to be 300 psi or 2069 kPa, 650 Fahrenheit, so it's quite hot. And we're at 343 degrees. So that's our setup to our problem. So let's look at this assessment here. We've got a repair history that's given to us from the inspection group. The groove-like flaws are located 20 inches apart from either side. Each of the groove-like flaws is located a minimum distance of 36 inches away from the nearest structural discontinuity or weld. Based on the process conditions and a visual exam was determined that both grooves were caused by fluid erosion. And we have one here, and then we have the second flaw. So it looks something like that. So we're going to call the top one groove 1, and then we'll call the second one groove 2 for records. And basically, when we go through this example, we've got to basically go through, do groove 1 analysis and then rigorously go through groove number 2. And over here is a little bit of information we have about our weld, and that which is our discontinuity, and we can take that into account in our calculations. Okay, so we've gone ahead and we've taken our data from the previous information. We've organized this in a good way so that we can, easily do the calculation if we choose to do it on Excel. So here's our vessel. Of course, all this information is important to determine what your allowable stresses are if you need them. And in this case we do. And we talked a little bit about the joint efficiency factor, about because that is taken into account in the calculation. We have some dimensional information here. We've got the future corrosion allowance that we have to consider when we do the analysis, because we want to determine whether we can go until the next turnaround. So then the distance to the nearest structural continuity, we've got our pressure and temperatures, which we've stated here, in one in metric and one imperial. And we have negligible supplemental loads. Because if we recall from an earlier video, we sort of have to think about, what kind of component is this? Well, in this case, we don't have any supplemental loads, and it's purely a pressure one. So this is really like a type of component. And in this case, it would be totally justified in this example to work on a level 1 analysis. After we've analyzed and looked at the data, received the data from the operating conditions and so on, we have to really look in depth at the inspection information and get that organized. Recall that we had 2 types of grooves, so we've organized them. The orientation is in the longitudinal direction along the vessel. And we have the groove widths as shown as 1.5 inches. They're both the same in this example. It's just to simplify the analysis. But the depths are different. So we're going to look at, basically we're going to look at this depth, and we're going to look at this one. Of course, intuitively we can see that groove 2 would probably be the one, but it will be the one that's the most severe. The lengths are both the same. The radiuses are a little bit tighter. Not, right here it's very tight, so we would expect, to be issues. And then we have a few other issues here. We have a remaining strength joint factor of 0.9, and recall that's from chapter 2, and because we're using a pressure vessel, we're justified in using remaining strength factor of 0.9, and of course this is the distance to the discontinuity, the LMSD, and these definitions are all part of the definitions as spelled out at the back of chapter 5. Part 5 has a whole bunch of different flaw shapes and basically a catalog of different scenarios. And so when we go into our catalog and look in the back, the closest match we have is a groove-like flaw and a plan view. So these are the kind of information such GL, the groove length, the thickness, right? The Tmin, the minimum TMM, the minimum thickness, and then the radius and the width of the groove. So we can go through the catalog and we can find some other information. This is a cylindrical shell or a pipe. That's our example. So we've got hoop stresses and longitudinal stresses on our stress field. It's under pure pressure, no supplemental loads. So again, this is our what it's defined as our circumferential orientation. This is our axial longitudinal one. And recall earlier that we were told all of our grooves are longitudinal. Now there's some tables where we can analyze a bit that's at an angle, and the angle beta, and we can use the analysis, because in reality we don't always have flaws that are running perfectly perpendicular or circumferentially on a part that we're evaluating. So there's some additional steps that can be taken. I threw this slide in here just to be a reminder where we got our remaining strength factor allowable. We got it just basically from the code. It's pretty straightforward. I mean, they're all basically at 90%. So If you look in chapter 2, there's under remaining strength factor, there's a very detailed discussion, lots of strength and materials discussion. So it's a little bit involved, but I'm glad that they've simplified it with this table. So now we're going to go ahead and perform a level 1 assessment because it's a type A part. It's just in pure pressure. And so we would follow section 5.42 in either editions, which one you choose to work with. And it's the same analysis. So we're going to look at these kind of flaws. So let's dive into it. Analyze this and look at the standard over and above what the example gives. So if we go to section 521B1, there's a flaw classifications, which we talked about in episode 1. But so it's a groove-like flaw, okay? The flaw length is much greater than the width, and that's exactly what we see. So this one's pretty straightforward, and we have a sharp radius that may be present at the base of the groove-like flaw. There's a reduction in the wall thickness. This is all true, and the material has been cold worked, inside the formations because of gouging and that kind of thing. And it's caused by mechanical damage, dents and gouging. So there's another section on that, but we're going to focus on this for our analysis, which is the groove-like flaw. Now this is an interesting one because a diagram because it gives us some advice about our longitudinal weld seam, our distances from your circumferential weld seams. It gives us the local thinning area, talks about S and C. It introduces those terms, and we saw similar terms with the LTA, right, the local thinning, and so basically, these are some overlap here. And so with the local, whether it's an LTA or groove, we have to identify, our subject area of inspection. So this is guidance. So when we do our inspections of this groove, we need to be over and above that, if practical, of course, to get the full thing. So to make sure that there's nothing else there. So this is what API asks for. Okay, we're going to go and calculate step 1, which is 5332, excuse me, and we're going to determine the critical thickness information and what we need to do. So S and C is calculated with this equation, and every case is different, so you have to look at the geometry. This is just a geometry relationship, and because beta is zero because it's all longitudinally, then basically one of these values cancels out, right? And then you're basically left with, this one on this one and that one on that one for 0. So then you calculate S and C, and away you go. And that's how you get that. And then from there you can determine, the size of the inspection area that they need to perform as well. Once we've worked through equations 5.1 and 2 to describe the orientation of the flaw, we have to look a little deeper at the wall thickness. And so there's a couple different formulas that we need to look at the depth and the size of the groove, the grooves, the cross sections. The first one is we calculate TRD for the nominal thickness minus the corrosion allowance, and then we take that value and we subtract the future corrosion allowance to get our predicted values, and that's equation 5.4. So in this case, we are going to use 1.25 for part of this analysis, as we'll see in the next few slides. Okay, so we're going to determine the minimum measured thickness, TMM. I'm not sure why they use TMM. I would have used TMin, but that's the nomenclature they use, so we got to stick with it. So S, dimension S, and then we're going to calculate the longitudinal CTP. So let's jump into this. So what we're going to do is we're going to look at their shapes, and so we can get a sense of where we are, and you can recall from our calculation, our TRD is given there. And so then we have our other dimensions which we determined, and we can just take a look at this a little bit better. So then we determine T minimum for groove 1 is RTD, which is here, which is what's left in the material. We're not considering the future yet, minus the groove depth. And then we get this, which is 0.65. So that's what's left. That's our minimum thickness in our groove. So we got to go and look at its cousin, which is groove number 2. So groove number 2, a little different. We've got 0.65. Now our groove depth, our critical thickness is 0.475. So I suspect this is going to be the critical one, but we can go through the steps and make sure. So groove 2, and we calculate our T-min to be 0.475. Let's continue. Now we're going to use equation 5.5 in our procedure. And step 4A, determine the remaining thickness ratio. This is really critical. This is used quite a bit in the different areas. And so basically you take the the minimum thickness minus the future corrosion allowance over TC to give us this remaining thickness ratio to see if we did wait till the next turnaround, would we have a problem? And then we would do the same kind of thing with the second thickness. That's why I call it T1 and T2. So you can see that we require this ratio to be down to 0.35. It's going to be tight. We need some more information here. So we got to find our outside diameter. So we determine it from this equation. We take our corrosion allowance plus our future, and then we get this outside diameter. And then we just basically take the longitudinal flaw length, and we determined these values early. We got that from this value from up top. And then S value, recall we got earlier, so that's our D is here. And S from the previous slide, and we have also determined TC. So we determine our flaw length right there. So in AP step 5, equations 5, 7, 5, 8, and 5, 9 are just checks to make sure that these equations apply. So we first check is we check whether that if that ratio is greater than 0.2, because if it doesn't, then we can't apply level 1, and in our case we're good. And then we go to equation 5.8, and here's a criteria for pressure vessels. They use this equation, and then in 2007 they divided it out and they created a special equation just for that. And that's what you'll see in the 2017. You'll see more like being more differential evaluating the components. They were sort of grouped in the earlier versions, and so in the attempts to get a more accurate answer. So but anyways, we checked, even if it's a vessel, it's a pipe, it's still level 1. And the last one is we're going to look at that distance from to our weld, right? Discontinuity. And in that case, we're good. In the earlier version, 2016 or 7, excuse me, it's 2007. We're following 5.9, and the 17 we're following 5.10. So let's proceed to step 6, crack depth assessment. A reminder that step 6 is not applicable to the LTA that we did in the previous episode. And so if we pass, then we proceed to step 7. If we fail, then we have to consider this as a crack-like flaw, and we should actually go to part 9, which is the crack part. And so what we're doing is we're just checking to make sure that this groove is really a groove and not a crack, because the rules are very different. So in this case, our crack depth should be approximate equal to the groove depth when we do the analysis, and the crack length is the groove length. So these are the criterion in which we would follow if we were to go to part 9. We would have to do this little conversion factor before we would jump in. Okay, so I've analyzed the grooves 1 and 2 together. So you see that we use the same equation. So in groove 1, because recall we have a thicker minimum part, we actually pass this equation. So we're okay. We can proceed to step 7, and the other one where we failed. So we have to proceed to part 9, because in this case it's probably considered to be a crack, like an assessment with a crack. Or so that's what they're saying in the specification. So now we're ready to do our MAWP for groove 1, and recall that we have to do one for each one. So here we calculate our outside radius. We need that. We don't have any supplemental loads, so we can continue. So basically we've just got the hoop stress equation, and so we calculate that, and the 579 has a section for that to follow, so we just follow that rigidly, and then you don't have to worry about making some kind of conversion error. And as long as these criterion pass, then you can use this equation. In our case, we're okay. So we did some validation checks to see whether we're doing okay for our circumferential. We did some validation checks for the longitudinal, and we found our longitudinal stresses for each one. Of course, one is almost half of the other, which is exactly what we would expect for the stresses, right? And basically then we take the T minimum, and in this case, we're limited by the circumferential stresses, which makes total sense. And we get 383 psig. So we're going to analyze the longitudinal extent of the flaw for groove 1. So we're going to this table that we have is figure 5.6 level screening table. It's a nice table. It just gives you a quick assessment. It's good for inspector who just, they're in a hurry. They just include this in the report. And as long as you have to match the geometry. So in our case, we have a cylindrical shell. So this is the table we would use. And from there, we calculated earlier from step 4, we had 1.0821, and that's step 4. And then we have our RT, which we calculated again from step 4, our thickness ratio. And then we just apply it to the graph. So we've got our value there. And then we calculate our MAWP required. And there's our thickness ratio. So it's telling us we have to do this MAWP calculations required. We have to go further. If we were, for example, up top, then we would over here. Then we wouldn't have to continue. But because we're in this area, we have to do more analysis. Okay, step 8, evaluate the longitudinal extent of the flaw. I mean, you can go to Fable 5.2, Note 3, and you can follow some charts, do some interpretation, or you can go in do the calculation MT. I mean, I've done it and I calculated 1.2887. The calculation is quite intimidating. It's like that. And you also have to put some if statements in your spreadsheet to make sure that, you're applying this properly. But, I've got it in there and the computer can certainly digest that. And anyway, so that's the flaw factor that was developed by API to work through this problem. Okay, so we're going to continue with this here. This gets easier after we get the flaw factor done. So we're going to determine the remaining strength reduction factor, so we can determine whether this is, okay. So we use that equation, and you can recall down here we used MT, and of course our thickness ratios, and so that's not too bad. So we calculate that, we get an RSF of 0.897. So as we wrap up step 8, we make our adjustments based upon the ratio, strength reduction factor ratio, to adjust for our required MAWP. And so when we do that, we get 369 PSIG. Now we go into step 9. We evaluate the circumferential flaw this time. And so we have to determine the C value. And we drop right into this equation again, and we get 0.23 for our lambda circumferential. Now we go into 9.2, and we do the same check as before with the longitudinal, but we check these equations. So, this has got to be less than or equal to 9, and it's true. So we proceed to 9.3. We have a ratio of the diameter. Check 1 again, and then our remaining strength factor. There's some criterion to follow, and then there's criterions for 3 and 5, which is the weld joint factors, right? Because you may not have it all radiographed, and it might be 0.85, but in our cases we're good, so we can proceed to the next. So let's look at the second chart. Recall we did one for the longitude. Now we're doing one for the circumferential extent of the flaw. And so we need to match our geometry. So figure 5.8 is the one that would work for a level 1 assessment for a cylindrical shell. Some of the data that we need for this is lambda C, which is basically 0.2 for this graph from step 9. We need our T as 0.55, and as long as basically we need it to be over here. But let's see how we do here. So we've calculated that our TSFA earlier, it's in this range, so we follow down this curve here, and then it follows along here. Okay, so let's continue. So we do the math. We've got our lambda over here we calculated approximately, and then we do that, and we determined that the circumferential flaw is acceptable because RT is 0.55 and all we need is 0.22. So we are good. Last, we are done. Groove 1. What can we say about Groove 1? Well, we can say Groove 1 is acceptable. We've looked at it and we're fine. The MAWP we estimate to be at 369 PSIG, which is greater than what we needed, because we recall from our first charts that we had to be hit at least 300 PSIG at the design pressure. So we're fine with that. So conclusions for Groove 2. The vessel is not acceptable for continued service. We've got to change something, or we have some other ideas. So the groove, and this was all based upon a level 1 assessment. So when we do the screening, we talked about how, if it doesn't meet it in earlier steps, we can consider it like a crack-like flaw, and hence we can do an alternative type of analysis. And so therefore, a Part 9 evaluation could be considered.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.